Hi there. In this video I'm gonna do a couple of examples of section 3.5, graphing polynomials. So we already know how to graph some of our polynomials, like y equals x squared. This is a parabola, and when we did it by plotting points. But now we could also do it by looking at the vertex. The vertex, this has the form, right, if you think of it. Some of the forms we've talked about, this is, the vertex is 0, 0, and there's a positive in front of the x squared, so it opens up. So y equals x squared. We've also know how to graph y equals x. So y equals x is our basic line, slope 1. And so these are polynomials. So a polynomial is something that has x to a power. So examples of polynomials, you could have y equals x squared plus 2x plus 1, y equals any linear equation, y equals mx plus b, right? So by that token, any quadratic, y equals ax squared plus bx plus c. So polynomial is the sum or subtraction of sum or difference of terms. So you could have something like 5x to the 7th minus 2x to the 4th plus x minus 17. So these are just examples of polynomials. So a polynomial has to have a term, so a coefficient, and an x to a power. So and the power has to be a whole number. 0 or positive. So notice that the constant term is really 17x to the 0. Anything to the 0 power is 1, so we don't see it. So constant terms are still polynomial terms. So how do we graph other polynomials? So I'll start with graphing y equals x cubed, to give you an example of something other than a quadratic or a linear. So this is where we're going to graph it, but we're going to go ahead and choose some points. So I'm going to go with my standards, minus 2, minus 1, 0, 1, and 2, and plug it in. Y equals x cubed. So when I plug in negative 2, this is minus 2 to the third, which is, right, minus 2 times minus 2 times minus 2. Negative times a negative is positive, times a negative stays negative, and 2 times 2 times 2 is 8. So negative 8. Do the same thing with minus 1. I'm going to get minus 1. 0 cubed is 0. 1 cubed is 1. 2 cubed is just 2 times 2 times 2, which is 8. So it's looking like at minus 2, we're going to be all the way down here at minus 8. At negative 1, you're at negative 1. 0 is 0. At 1, you're at 1. And at 2, you're going to be way up here at 8. And the way that this graph looks is, I'm not doing it justice here, but this is the parent graph, y equals x cubed. So it's I call it the John Travolta function. If you think of Saturday Night Fever, where he does the move with the hands. So this is the John Travolta graph. And just like with any shifts, right, so if I graph, like we did with parabolas, if I graph y equals x cubed minus 1, it essentially takes that parent graph and is going to move it down 1. So it's going to be at minus 1. So it's going to have that little curve here, but it's going to happen at minus 1. If I graph y equals x cubed plus 2, where is this curve going to happen? And that will happen at 2. So it's going to shift up 2. And just like with parabolas also, if the shift happens on the inside, right, if I have x minus 1 cubed, this then is going to be a horizontal shift. So it's going to move to whatever makes that 0. X minus 1 is 0, when x is 1. So it's going to move to 1. So that's where the change in the curvature is going to happen. So this is a pretty basic cube. When you have things that look slightly more complicated, like x to the 4th or x to the 5th, and those x to the 4th looks like a parabola, but we can make use of our graphing calculators as well to graph. So for example, say I wanted to know y equals x cubed minus 4x plus 2 is going to look like. Now this doesn't look like any of those, right? If I just have x cubed and a constant, then I can say, well, this is just a shift, either a vertical shift or a horizontal shift on the parent graph, the John Travolta function. And this one has something else going on. So I don't know what this is going to look like. So this is where our graphing calculator comes in handy. And so we're going to go to our graphing calculator. So let me go all the way to the menu. So when you're at the start, when it's blank, you want to go to y equals, and there should be nothing there. If you have something there, just clear whatever you have in there, and we're going to start typing our equation, which was x cubed minus 4x plus 2. So I'm going to say x, my variables are here right under the mode. If you have a TI-84 or any TI, the format should be the same. You can also download the TI-84 app for your phone. I think it's $4.99 for the app, and I believe there's a free one somewhere. So we're going to go, the variables are here, so x, and then the exponent is the caret, so go at caret 3, so x cubed. And notice that my cursor is still at the exponent, so to bring it back down, just hit the arrow, any arrow, either side or down arrow, and it brings it down, and it's minus 4x, so I'm going to press my variable again, plus 2. And we're going to graph it. And there's my graph. If your window is a little weird or it's off or is giving you just part of the graph, you can go to zoom and press the number 6 for standard. So if you press 6, it gives you back to the standard window. The standard window is a 10 by 10. So it goes 10 positive, 10 negative, 10 up, and 10 down. And so this is what this graph looks like. So to the best that I can, I'm going to try to copy it, and notice that from here I can tell that the y-intercept is going to be a 2. Remember, the y-intercept is when x is 0. To find the y-intercept, you let x equal 0 and find y. So y is 0 cubed minus 4 times 0 plus 2, which is just 2. So the y-intercept is at 2, and so now trying to draw that, I know it's going to cross, so that must be a 2 where it crosses. So it looks like it's doing oops, I didn't draw it very well, but you get the idea. So that's what this guy will look like. And it goes on forever. So notice that this is a cubic, and it crosses the x-axis according to our graph 3 times. So it crosses there, there, and there. So those are the x-intercepts. So this has 3 x-intercepts, which makes sense. So a polynomial has at most the power of the polynomial in terms of roots. So x-intercepts are also called roots of the polynomial. to find an x-intercept or to find the roots of the polynomial is when the equation is equal to 0. So anytime you want to find roots or x-intercepts, just set your whole equation equal to 0. So a polynomial has at most the number of roots of the highest power and the degree of the polynomial. And notice that it has a peak and a valley. And so let me say, if you have a polynomial of degree n, so something like that will look like a n x to the n plus a n minus 1 x to the n minus 1. This is the general form of a polynomial. Right, so you go, so something cube, like in this case, if I want to write this cubic in that form, it will be y equals 1 x cubed. Notice that there's no x squared, right? There's no, the 1 degree less than. My highest degree is 3. This says 3 minus 1, which is 2. So there isn't one, so I can put 0 x squared minus 4x plus 2, kind of like a placeholder because there isn't a quadratic. But in this case, a sub 3 is 1, a sub 2 is 0, a sub 1 is negative 4, and a sub 0 is 2. So if you look at the general form of a polynomial. So this is a polynomial of degree n. So it has at most, so the most it can have is n roots or x-intercepts, and it has at most n minus 1 peaks and valleys. So notice that this has 2 together, so that's a peak. Think of a mountain, and that's a valley. Think of Sacramento and like Tahoe. So that's why Sacramento region is called the Sacramento Valley, right? We're the bowl in a bunch of mountains. So peaks and valleys. And so essentially a polynomial of degree n has at most n roots. It doesn't have to have n roots, but it has at most, right? Notice that when we did this is a polynomial of degree 3, but we only have one root, one x-intercept. So you can have at most 3. So if you ended up with 4, that wouldn't be possible for a cubic. So you can have 3, you can have 2, you can have 1, and then you're gonna have at most n minus 1 peaks and valleys. So this one had no peaks and valleys, and this one has exactly 2 peaks and valleys. So that's a little bit on polynomials. So let's see. Let's do an example of how to graph one. So let's graph y equals, and I'm going to give it to you in factor form, x minus 5 times x minus 1 times x plus 1. So if I was to multiply this out, this is going to be a cubic, right? So if you FOIL this out, use the distributive property, and then once you have that quadratic, you distribute it with the x plus 1, you're going to get a cubic. So this has, this polynomial has degree 3. So that means it has at most how many zeros? The same as the degree, right? So it's going to have at most 3 zeros, and at most how many peaks and valleys? It's going to have at most n minus 1. So 3 minus 1 is 2, so it's going to have at most 2 peaks and valleys. So how do we find the zeros? right? We find the zeros or the roots or the x-intercepts. So the x-intercepts have lots of names. Zeros, roots, x-intercepts is when y equal to 0. So you set your whole equation equal to 0. So set x minus 5, x minus 1, x plus 1 equal to 0. And this is why it's nice to have it in factor form, because then I can say, oh, remember the zero product property. If you have things being multiplied equals 0, one of them is 0. At least one of them is 0. So either x minus 5 is 0, or x minus 1 is 0, or x plus 1 is 0. So our roots are x equals 5, x equals 1, or x equals negative 1. So when you go graph it, we want to put those guys in there. So negative 1 crosses the x-axis there, crosses the x-axis at 1 again, and then it's going to cross it again at 5. Okay, so now I have the zeros, but how do I know what it looks like without using my calculator? Right, when I used this one with my calculator, because it wasn't factored, I saw these. Now I will have to do some long division here and try to guess at some of the roots and do long division to algebraically find those guys. Here we're doing it the opposite way, where I'm giving you the factored form, and so we can find the zeros, but now I don't know how it looks. So this is where test points come in. So we're gonna use test points to see how the graph moves. And so I have so I have this region, so that's considered an interval. I have this region, so that's 2, 3, I have 4 intervals. So we're gonna look at our intervals. We're gonna pick a test point. And we're gonna see what the function is doing, what the graph is doing. So my interval, my first one is going to be when x is less than negative 1. So when x is less than negative 1, pick a test point. What's a number that's less than negative 1? We can pick negative 2. And then see what the y value is going to be, right? I know that y equals x minus 5, x minus 1, x plus 1. So when x equals negative 2, what does y equal? Right, so I'm going to have negative 2 minus 5, which is negative 7, minus 2 minus 1, which is negative 3, and minus 2 plus 1, which is negative 1. Now, we don't really necessarily care too much about the actual value, but about the sign. So when I do this, I'm going to have negative 7 times negative 3 times negative 1. So negative times a negative is positive, times a negative is negative. So I'm going to get a negative. It's still going to end up being negative 21, but I really just care about the negative, because then I know that in this range it's going to be down here. So that means that this graph is coming from down below to my 0. And then, so I know it's negative. You can put negative 21, but that's going to be hard to plot, so I just know that it's negative. And now let's look at the next interval. Is from negative 1 to 1. So in negative 1 to 1, let's pick a test value there. And to be nice to ourselves, let's pick 0. Doing math with zeros, it's fun, unless it's in the denominator. So when x is 0, plug it in. So 0 minus 5 is negative 5, 0 minus 1 is negative 1, and 0 plus 1 is 1. So now notice that I have negative times a negative is positive. I'm going to end up with a positive 5, but all I really care about is the sign. So I'm going to put my test point is 0, and the value is positive. So in this case, I guess in this case I can go all the way to, and then see my graph is not looking the beauty of whiteout. So I'm gonna cross there, and it's positive, So notice that as I come from the negative, I have to cross there. I have to keep going, go into the positive, because this tells me, so it switches from negative to positive. But as I cross there, I have to come back to 1. So then it's going to have to go down. And now let's see what happens between 1 and 5. So when x is between 1 and 5, pick something in there. So you can pick 2 and plug it in. So when x is 2, y equals 2 minus 5, 2 minus 1, and 2 plus 1. And again, we care about the sign. So that's going to be negative, that's going to be positive, and that's going to be positive. So negative times a positive is a negative. So it's going to go back down. So it's going to go from positive to negative. And then it can't just keep going down, because from 1 to 5 I'm negative, but we have to come back to 0. So it's going to end up doing something like this. And then when x is 6, but we can kind of see without even doing the test point that this is going to keep going. But you can do the test point. So there will be 6 minus 5, 6 minus 1, 6 plus 1. And everything now here is positive. So you end up with the positive. And so that's how you graph a polynomial. If you can find, if you know if it's in factor form, you can find the roots, the zeros, the x-intercepts, whatever you want to call them, and then use test points in each interval. So your zeros break up the number line into intervals. So if you have 3 zeros, 3, you're going to end up with 4 intervals. If you have 2 zeros, you're going to end up with 3 intervals, and so on. So that's however many test points you need. Our last interval was x greater than 5, and we picked 6, and it was positive. So you can kind of see how it goes from negative to positive, and then this is between negative 1, 1. So because it's between negative 1, 1, it has to come. It's still positive, right? But it has to come back down to 0, and then it switches to negative, and then to positive. So that's graphing polynomials in section 3.5.